Here's part 2 of our lesson on modeling with trig functions. You may remember from the last lesson that we could find the c value by finding the vertical shift, which is just the axis of the curve, max plus min divided by 2. We could find the amplitude by doing max minus min divided by 2. That's just our a value. We could find the k value by sorry, let's keep my colors correct. Find the k value by taking 2 pi divided by the period, and then the phase shift, the d value, our horizontal shift, depends on whether we do sine or cos. Sorry, I realized I used the wrong color there as well. A, K, D, and C. Okay, that matches the colors I've been using up to now. Anyway, there's our basic sine and cos curves. Notice how it doesn't have pi on there, it's got numbers, but you may also recall that one cycle is 2 pi. And if you multiply pi times 2, you'll get 6.28-ish. And that is pretty much exactly where we are here. So everything does still match up. 1 pi, this would be about 3.14, and so on. All right, let's start by doing regression. We'll do a Desmos activity. So just follow along while I show you how to do regression. You've probably seen it in previous classes, previous courses, but in case you haven't, it's not hard. So I'll fire up Desmos, and I'm going to do a table. So I'll hit the plus button, hit table, and then I can enter all my values. So I guess I didn't actually read to you what the problem was. This one has to do with daily temperature by month throughout a year. So January is month 1, February month 2, March month 3, and so on. So that's the first column. And then they got the average temperature for that month. So the average temperature in January was minus 14, and February is minus 12, and so on. So that's our relationship that we're going to graph. So month 1, enter, 2, enter. One of the nice things about Desmos is it starts to predict things. So you can see it predicted the 3. I can just keep hitting enter until I get down to 12 because it matches up. I can't do that for my y values though, because they're a little bit more all over the place. So minus 14, minus 12, minus 4.9, 3.2, 11, 19.1, 22.4, 20.6, 15.9, 8.3, negative 1.7, and negative 10. Another nice thing about Desmos, before I hit it, is if you look to the very left of the screen, you'll see a magnifying glass with a plus sign on there. If I touch that, it's going to make my scatter plot fit the screen. Here we go. There it is. And so you can see it makes a nice sinusoidal type curve. Now, the way we do a regression is we want to make up an equation that ties this table of values into the equation. So you'll notice, if I go, let me just go back for a second, the headings of these columns are x1 and y1. So I need to get that in there. So I'm going to use x1 and y1, so I'll say y1, it automatically makes it as a subscript. And I'll use approximately equal to that squiggle. It's on the bottom row towards the right. Means approximately equal to. Now I'm going to use the transformation formula, a, k, d, and c. I'm going to make this a sine one. So I'll go a sine. I could type in sine and it'll recognize it. Or I could, if I didn't want to do that, I could also go back to here and go to functions, and I could pick sine from that as well. So either way I can get sine in there. K, I'm just going to use the same letters I always do. Bracket. I need to use the round brackets. Other brackets act kind of funny. X1 again, minus D, back to my round brackets, bracket, bracket, plus C. And there's my graph. And you can see it says parameters. A equals 18.2733, K equals 0.5, etc. D equals 4.11, and so on. C equals 4.0549. So those are my A, K, D, and C values. They're my vertical stretch, my horizontal stretch, my vertical shift, my horizontal shift. Yeah, not in that order. It's easiest to see if I actually put the axis of the curve on there. So the axis of the curve is going to be at where my C value is. So if I actually put in C equals 4.0549, there's the axis of the curve, and you can see how that divides, goes down the middle of the graph, divides it up nicely. And you can also see that the point of intersection here is 4.11. Normally a sine curve will start right there at that dot that I've identified because it's going upwards. That's the usual beginning of a cycle. So if I want to see what horizontal shift or phase shift occurred, I have to move it back 4.111 units to get back to the x-axis. And then if you look at the D value on the left, you'll see that does match up with that. The amplitude is 18.27, which goes from the 4.055 up to whatever the highest is, around 22.4. That's where you get your 18 from. Your K value, remember, it's normally a period of 2 pi, which is the same as 6.3, let's say, units. So if we have a K value of 0.5, that would double it. And yeah, lo and behold, our period is approximately 12 units long. If I go over to about here, that's about where one cycle is, right? Somewhere around here. And yeah, it's about 12 units on the x-axis. So everything matches up. So we can do an equation nicely from a table of values using Desmos. So let's just record those values and then we can move on. Y equals 18.3 sine 0.5 x minus 4. Let's just call it 4. I'm rounding a little bit, right? I guess I could go, 4.1 maybe, plus 4.05. There's the equation using regression. Okay. Second example, passengers on the London Eye Ferris wheel board their pod at the bottom of the circle at a height of 5 meters above the ground. One full rotation takes 32 minutes and the passengers reach a maximum height of 135 meters. All right, so this is important information. This gives us the period, and this is the maximum height here, of course. Model the height of a passenger over time using sine and cosine functions. So we want to use both in this case. So let's start by doing a labeled sketch. So if one cycle, let's draw an axis on here. So if one cycle is 32 minutes long, then if I go up by 2s, this would be 8, 16, 24, 32, and this is time in minutes. And then the height is in meters. And if I go up by 10s, then we got 20, 40, 60, 80, 100, 120, 140, 160, and then 170, I guess. We don't need to go quite that high, though, do we? Because we're only going up to 135. All right, so there's my scale. And again, we want to assume that people get on at the bottom. So they're going to get on at time 0 at 5 meters high. That means that if they're going to be halfway through the ride at 135 meters at 16 minutes, they'll be back down at 5 meters at time 0 again. Sorry, time 32. So we can do things like we can calculate. Let's start with the C value. I always like to have that first because then I can put my axis of the curve on there. So 135 plus 5 divided by 2 is 140 divided by 2 is 70. So the axis of the curve is going to be at 70 meters. So I'll do a horizontal line here. And that way I can easily say, okay, we've got to cross that line at 1/4 of the way, cross it again at 3/4 of the way, draw my sketch. There's a rough sketch of the curve. And then I can come up with, I've already got my C value, I can get my other values pretty easily as well. So the A value is the amplitude from 70 to 135 has got to be 65. I can just see that, or I could calculate it. My K value is going to be 2 pi divided by 32, which I'll just leave as a fraction as pi over 16. And my D value is going to depend on whether, what kind of shift I'm doing. So if I want to do this as a sine function, move this h down here, it's going to be y equals 65 sine k was pi over 16 bracket x. Now, how much to move from here back to here? Because that sine always starts on the x of the curve. Well, we're moving it back by 8, right? So it's going to be, we're moving it back by 8, so it should be a plus 8. Sorry, I moved it the opposite way. This is the actual curve. So sine normally would start on the axis of the curve. We're moving it forward 8, so it should be x minus 8. My bad. Sometimes if I go too quick, then I get whether it's plus or minus, which direction are going mixed up. So plus 8, sorry, D is plus 8, and therefore we're moving it, when we put it in the equation, it becomes a minus 8. And then C was plus 70. So there's a sine function. Cosine, y equals exact same thing, 75 cos, and it's pi over 16 again. Now cosine, I could either go this way, so it would be x minus 16 plus the 70 still, or we could instead do it as a reflection. I could go 65, I could make a negative 65 and instead think about this point here as a starting point, but as a reflection in the axis of the curve, and therefore don't have to do any horizontal shift at all. It's just negative 65 cos pi over 16 x plus 70. So those are 2 cosine and 1 sine equation for this function. At what times is a rider at a height of 120 meters? Okay, well, the output is 120, so I can pick any one of these equations and then just solve it for what's missing. So say I took the sine one. I took this one here. Y value, again, I should have used h and t. Let's just replace those in this one at least. Height and time in this equation. So I've put a height in 120 meters in here, and then it equals 65 sine pi over 16 x minus 8, sorry, t minus 8 plus 70. Then I can solve this equation. I can rearrange it and solve it. I can see from the graph approximately what it's going to be. If I go to 120 and draw a line across here, we can see it intersects this graph at approximately 12 minutes, 12 and a bit minutes, and a little under 20 minutes, right? This is a 16 here, so it's a little under 20 minutes. So 12 and a bit minutes and 19 and a bit minutes. So we could estimate it from the graph, or we could rearrange this equation and solve it. So I could isolate t in this function. I'm going to just go with what I've calculated before from rearranging it because I don't have a lot of time. There's 2 solutions though. x1 was 12.47 and x2, or t1 and t2, I'm going to force myself to use the proper variables. t1 and t2 is going to be 19.53, and that's minutes. There's 2 answers. There's 2 times when this ride is at 120 meters. The first one is when it's on its way up. That would be the 12.47 minutes, and then back on the way down, 19.53 minutes. What parameters would change if the entire wheel were raised by 7 meters? Let's imagine somehow they put it up on top of something. All it does is move the vertical shift. So the C value would change. It becomes 7 more than what it was. It was 7, so it becomes 77. What's the radius of this wheel? What parameter does the radius correspond to? The radius actually corresponds to the A value because that's the distance from the axis of the curve. The axis of the curve is going to be right at the axle, and so the A value is the radius, and the radius is therefore 65 meters.